Hi, and welcome to my talk, Implementing Machine Learning Workflows on Nomad. I'm Max Fröhlich. I work as a platform engineer at Serviceware. We take care about a lot of DevOps-related topics all around the HashiCorp stack. Prior to that, I was working as a software developer in our machine learning team, where I supported our data scientists building and deploying applications to our Nomad cluster. At Serviceware, we make service for the enterprise service management. That means we provide a platform for IT, HR, finance, facility services for large enterprises. We have a very diverse tech stack from Python, Java, .NET, Go, JavaScript, you name it. And we use a lot of things from the HashiCorp universe. Many of our products produce a lot of data, and therefore, a few years ago, we set up our own machine learning team to help bring more and more AI-enhanced features into our products. We do this in a close cooperation with the Technical University of Darmstadt. So, machine learning compared to classical programming, where in classical programming, a developer writes an explicit algorithm to solve a problem. That works for a certain amount of inputs. Let's say I only want to calculate the real estate price, and I take the rooms and the size in account. So that kind of works, but as soon the amount of inputs increase, that approach doesn't scale anymore. Therefore, machine learning, on the other hand, is where a developer feeds a program enough samples so it tries to figure out the algorithm by its own. The downside of this, that the results from those models are hard to explain, and also computing those models is very resource intensive. So in machine learning, we talk about these models. What are they? Very oversimplified, you could say they are just a function where you put in all the input parameters, and then every of those parameters is multiplied by a certain variable and then summed up. These variables are also called weights and are learned during the training while you feed your program those examples. Usually that's not a linear function, and those are very, very large matrix multiplications. In our team, we dealt with natural language processing. That's the topic where we try to teach a machine how to deal with text. There are multiple examples for natural language processing. One could be sentiment analysis, where you try to figure out what is the sentiment of a certain text. Let's say movie reviews, where you say, hey, that movie was great, and you can take away, like the model computes, okay, that was a positive comment. Another example would be intent recognition, where you try to figure out what the user wants. Let's say somebody writes, hey, I moved to New York and need to update my account. Therefore, you know, he wants to change his address, and you maybe want to guide him to the change address process. Another, I think, very popular topic right now is the generating text part, where you can use OpenAPI's GPT, for example, where you say, hey, write me a one-liner why HashiCorp's Nomad is the best choice for running machine learning workflows. And the model would go there and generate you a certain text. So from a more technical point of view, in natural language processing, it's about translating words and sentences into numbers and vectors. And then for doing that, first you have to do some text pre-processing. You have to remove unimportant words, and you have to deal with a lot of unexpected content also in your text. In our case, we had a rich text editor where we got user-generated content from, and while processing those texts, we just stumbled upon base64 encoded images, or even like embedded Office documents and HTML comments. And then there's the model training, which requires a lot of resources, especially CPU, preferably GPU, and a lot of memory. To put this a little bit into perspective, the GPT-4 model, which was recently released, contains more than 1 trillion parameters. These parameters are the weights we just saw in the slide before. So a workflow, how does its general workflow look like? It starts usually with some kind of experiment phase where you try out existing models, maybe where you do some proof of concept training of your models. You try out several configuration and just try to figure out what works for you. If you found something that looks promising, you start with the actual training. In the training is the part where you then actually compute the model. And then after the training has happened, you go there and in the serving phase and start creating new predictions on new inputs you haven't seen before. This usually is done via an API or something. Then when giving those feedbacks, you also start collecting feedback and try to track those for the next experiment phase. So now that we are all experts and expert scientists, let's first focus more on the training and serving part. In the training part, you compute your model, and then you store it. You do this by serializing all these metrics values, these weights and biases from these metrics multiplications, and serialize them somehow and store them with some pre and post scripts that maybe do some cleaning up, and then also translating maybe numbers back into more actual business functionalities. Then in the serving phase, you take those models and you deploy them with an API, maybe something REST-ish, where you say, hey, I have here my get endpoint, my get predict endpoint, where you pass them some inputs, parameters, and then you get some JSON back. In this case, for example, let's say, hey, the intent is change address, and we are 99% sure that this is what the user actually wants. So how did we start? What was our first approach? That was a very naive one, where we said like, hey, okay, let's just build an all-in-one application where the application holds all the data. It decides when to train and retrain a model, and it provides the API to serve new predictions. Also, alongside that, we have some small admin API where we manage our data and do just basic operations on the application itself. To store all that, we used for the regular data, we used a Postgres database, and we stored the computed models in an S3 bucket. How would this look like from a Nomad jobs perspective? It's just one simple job file where you have like one group with one application in there that holds all the that one container. And you can see already that this it takes a lot of resources in here when you look at the resources block. So this is actually a problem because especially the training requires a lot of resources, and the serving, on the other hand, should be redundant. So this really doesn't scale. So our next approach was splitting up the training and the serving application. So we can say, hey, okay, the training application gets more memory, and we could theoretically, if we would have a CPU, a GPU, we could decide, okay, we maybe need like really fast servings, therefore we give the serving application the GPU, or you could give the training because you want to have like fast computed models, give that the GPU. So you can do more efficient resource assignment here. The Nomad job file, just split it up here. You could see first we have the training group, and that still takes a lot of memory. But on the serving, which is now, we can already set the count to 3. So we can scale this application and deploy it high available. And this one just takes less memory. There's still a problem that you have some application deployed, which is most of the time actually idle, but still allocates a lot of resources. So the quick hack we did was use memory hard limit of the Docker config. So this allows us to limit in the resources block, actually reduce the amount of memory and tell the orchestrator, hey, okay, that application doesn't need that much memory. But if it needs to do a training, it can go up to 32 gigabytes. This at least helps you to free up unused memory in the idle state. But you still have a new problem if that allocation is hosted on a Nomad client that is already at max capacity when it comes to memory. your application potentially may crash, and you want to avoid out of memory exceptions. So the third approach we took was a more Nomad cloud native approach. So therefore we said, okay, the training task, as long as it doesn't do anything, it doesn't run at all, but we can define this training task as a batch job. Therefore, our admin part of the application decides when to trigger training by going to the Nomad API and tell it that it should dispatch one new training job. And this training job runs and it completes successfully. All the resources are completely freed again. So let's have a look here at how does this job look like. I just focus here on the training job because this is now not a service anymore, but this is of type batch. And the nice thing also about batch job is that you can register them. They don't use any memory while they're not in use, and you can even parameterize them. So when the admin application decides to run one training job, it can pass a load parameters that are then realized as a file in the location. So here, in this case, our training params JSON is in the end a file our training code can pick up and read parameters from it for that particular training. Just some words on advice here. Have something that limits the amount of parallel trainings you can do, because you might have a user somewhere in the UI that clicks 10 times in a row the training button, and if enough resources are on your cluster available, Nomad will just go there and say, okay, I'm going to run as many batch jobs as you like in parallel. And also, the admin application, since it talks to the Nomad API itself, make sure you limit its access by using ACL tokens. Okay. Now we are running and serving our models already in production and generating great business value. And now we collected also some feedback, maybe some thumbs up, some down buttons, or you have integrated some very smart analytics script that collect a lot of information on the given predictions of your servings. The data scientists are quite eager to get their hands on the feedback and try them, especially in combination with the data, try out if they can optimize the model and see how they can build it better and even more precise. Unfortunately, we had problems there. It is not that easy to do, just to go there and experiment. Accessing the data from outside the cluster is hard. You have firewalls in between. You have hopefully no hard-coded credentials. Also, for privacy reasons, you're maybe not allowed to transfer the data out of the data center. And especially storing this data on local machines is not allowed. Luckily, there's something called the Jupyter Notebooks, which is like a web-based interactive Python environment. It's a very commonly used tool for data scientists. It lets you visualize data. You can do all kind of interactive elements there, and you simply can program Python there. And you can run these applications inside your cluster, so it's quite close to your data. Still, in our case at least, we had some problems here. We had just like one big notebook instance running somewhere, and it was hard to figure out who is allowed to do which experiment and when, who installed which Python package. And yeah, in general, the access control was a bit tricky. Therefore, there's also a solution. It's called the Jupyter Hub, which is a multi-notebook server. Jupyter Hub itself acts as an application that spawns up and manages Jupyter Notebooks for you. So every user who logs into the Jupyter Hub gets its own notebook, and therefore you don't have any conflicts, and you can do even better resource sharing. How does Nomad come here into play? We built our own Jupyter Hub Nomad spawner, which then for each Nomad job you're going to, for each Jupyter notebook instance you're going to start, it's realizes those as a isolated Nomad job. So very basic overview here. The user logs into the Jupyter Hub with the Nomad spawner installed. The Nomad spawner goes to the Nomad API, schedules an isolated notebook via Nomad, and then it's data science time. So I want to give you a little demo on that. The first thing I'm going to do is start up my Nomad agent in dev mode. Everything worked fine. I should see the Nomad UI right here, and it looks promising. So in the next step, I'm going to apply this Jupyter Hub job I have here with my Nomad spawner image here and some configuration. I do this via Terraform. And now we should see some job coming up here. We see the Jupyter Hub spawning. This Jupyter Hub itself running. We can see it here. And if I open that up in a new tab, I get prompted some login UI. This UI is just a dummy demo UI for logins. You can easily exchange that for any kind of OIDC, OAuth authorization server login. I'm going to log in now as Max. And now I see my server options I have. So the first thing I can do is select the base image, the base Docker image my notebook runs into. I could customize this with any kind of Jupyter notebook I like. Could theoretically install some things if I like first in the image and have that pre-bundled. Then I can select the data center. I could select the memory amount I need. And then I'm going to start. So while this is starting here and coming up, we see in the Nomad jobs that there's a new Jupyter Hub notebook job running. And now it's data science time. So the first thing I obviously do, since everyone likes OpenAI, I'm going to install the OpenAI client. You see it connects and download things from for Python. As a next thing, I want to see if it worked. I'm going to OpenAI to import the OpenAI model. That seemed also to work. So now I want to get back to the example from my initial slides where I said like, hey, let's write a one-liner why HashiCorp's Nomad is the best choice for running machine learning workflows. And since I want to spice things a little bit up, I tell it to make it like a funny over-the-top commercial. With this message, I'm going to call the Nomad API directly, the OpenAI API directly, and tell them, hey, here's a message, please create a completion for that. And I pass in that message from up here. That seemed to have worked. And now we're really eager to figure out what's inside the reply. Therefore, I'm going to read the reply, the actual message somewhere a little bit hidden in this structure, but it should work. And now we print the reply. And here you see, if this doesn't convince you to use HashiCorp's Nomad as for your next machine learning projects, what else could? We can easily rerun this again. Just re-execute that cell, for example, and just do another one. So that's great. For any of you who may have used OpenAI, the OpenAI client already, you may ask, why does this actually work? Isn't there like an OpenAI API key I should use? Or I need to set it somewhere, and there actually is. So if I go here and say, and look at the environment variables, you see, grab OpenAI. you see an OpenAI API key, which I hopefully have revoked by the end of that demo. But where does that one come from? And the hint, it's not baked into the image itself. But here, when I was doing my initial Terraform apply, I also provisioned an OpenAI API key as a Nomad variable, which you see here is also present. And then what I did in my Nomad Jupyter Hub configuration here was I can easily modify the job template the spawner uses to provision any kind of environment variables or files via using Nomad's template block and render any kind of things I have either as a Nomad variable, or I could use a vault secret or something from console, and I can just easily customize anything I like here. So now that I'm happy with my experiments, I go back to the hub control, and if I'm going to stop my server, and immediately in the jobs you see it deletes and stops my Jupyter notebook, and it's not there anymore. So back to the Jupyter Hub, there are more pre-built features in there. For example, you have memory and CPU resource limits you can already configure in the options. You can set vault policies based on the user that logs in your Nomad spawner job file. There's even basic support for CSI and host volumes. And as said, the Nomad job is completely customizable via Ginger templates from Python. It allows you to control whatever goes into that job. Let's say you just read about Nomad's 1.6 feature of the node pool feature. So we say, hey, it's quite cool that all my Jupyter notebooks now can run also only on my GPU node pools. You can put this into your template. Or as said, like the very mighty template block feature, where you can just provision any kind of secrets, for example, use vault, use console, and so on. So ideas and feedback welcome. Check out the repository. But there are more challenges in the in machine learning workflows. One, for example, is load balancing, where you say, hey, okay, I have different models in production. How do I load balance between them in a smart way? How do I set up generic training pipelines? Also the topic of ETLs there. How do I do the tracking of models, and how do I collect the feedback? And there are a lot of more topics from the MLOps world. If you're more interested in MLOps, I can recommend ml-ops.org, where you find introductions in all the different topics. Also, the CD Foundation has its own MLOps special interest group. And there's also a great landscape from the Linux Foundation for AI and Data, where you can see a great selection of tools all living in that ecosystem. That looks like that, by the way. And our small Jupyter notebook is down here and mentioned as well. A lot of these products have something cloud native, usually Kubernetes flavored things on the wrapper. Therefore, some final words. Nomad has an API too. There's a lot of white space to claim for the MLOps topics in Nomad. Go hacking. Thank you.